Welcome back, everybody. It's been quite a while, I think, since we've done our last video podcast problem on physics, and here we are. We're in momentum and conservation of momentum, and we're dealing with a multi-part problem right here. This is example 10.7. And one thing I need to point out, first of all, the problem as it's stated in our notes here is there's a little bit of an error in it. It suggests steps for how to solve this problem, but as I see it, the steps are a little bit backwards. We have step 1: find the speed of the collision using conservation of momentum. That's our assumption that the momentum initial is going to be the total momentum final. Okay, well, we need to find the initial speed of the bullet. Okay, so we don't know what VI or VO is right here of the bullet. And we don't know what the speed of the bullet and this pendulum bob is afterwards, so we actually can't do this. We can't do step 1 first. So here's my whole point. We need to change the steps to make this step 1 right here. This is still step 2, and this is going to be step 3. We're going to be doing this problem backwards. So we're going to be starting here, and then going to there, and then doing this. And this is actually going to be probably a 2 or 3 part video because it's going to be that long. But it's all going to involve things that we know about. We know about conservation of momentum. The last few chapters we talked about conservation of energy. We're going to employ all these principles to solving this problem. And here's the idea. We have a bullet or some sort of a ball bearing being fired at this is called a bob, a pendulum bob. It's basically just a cup on the end of a pendulum or a string, the mass of which we're basically ignoring. This rod or string doesn't have any mass. And this bullet gets stuck in this cup, we're called the bob, and then the bob and bullet system flies upwards some distance. And we don't know what that actual height is, but we know what this angle is. We're told that angle is 42 degrees. 42 degrees from the vertical. Right there. So again, it goes back to the initial question of what is the initial speed of the bullet. That's why we can't solve step 1, what was originally called step 1 first, because we don't know the initial speed of the bullet. So let's start at step 3, which we're really going to call step 1, and then go to step 2, and then work backwards this way. So we're looking at this problem actually really as a conservation of energy problem, where we have this bob that has risen up some height right here. And what we really need to find out is what is that height? How high has that gone up? Why? Well, because we need to find out what the potential energy was that the bullet and pendulum bob gained by going upwards. So finding this height right here is critical to finding our potential energy due to gravity. You probably remember this from a chapter or 2 ago where we said the potential energy due to gravity is mass times gravity times, well, you can call it h, but we've been calling it delta y. Let's call this just delta y right here. You can call it h or delta y. But this should look familiar to you. mgy, mgh, mass times gravity times the height. Why is that important? Well, because this potential energy that the ball gains going upwards is going to be equal to basically the negative of, or the loss of, kinetic energy that the ball and pendulum bob have down at the bottom right here. And this kinetic energy can be turned into a final velocity of this whole system, and the final velocity of this whole system can be used with conservation of momentum to find the initial velocity of this bullet or ball bearing right here. So that's the idea. So our plan for part 1, which is right here, part 1, is to find out what the potential energy is that the ball and pendulum bob gain by moving upwards, and then we'll work backwards towards finding the initial speed of the bullet. So we know the mass of the bullet, and we know the mass of the bob. We don't know this height right here. We don't know delta y, or what's called h. So let's go about solving that. So let's draw our pendulum bob right here. Here it is vertically, and it's got this ball in there, and let's draw it at the angle to which it rises. Sorry, that's not straighter. Okay, the bullet is in there, and again, what we care about, I'm going to change to black here for a second, is this height h, or delta y. So probably the best way to do this is to turn this into, oh sorry, one thing I forgot to write in, we know this angle right here, 42 degrees. We know that angle is 42 degrees, and we also know, I should say, that the length, and we'll call this L, that is the length of this pendulum rod all the way down to the bob, is going to be 0.75 meters. So 3/4 of a meter. That's that length. Well, it also happens to be this length as well. Whoops, not even close to being straight. You'd think I'd be able to draw straighter lines having a graph paper here, but 0.75 meters. Okay. But what we want to find is this height change. I'm going to just keep calling it delta y from now on. This height change that the bullet and bob system undergoes by going upwards. So probably the best way to do this would be to turn this top part into a right triangle. Okay, so just draw a dotted line right there. And you may remember this from a problem that we did before, or a similar problem like this, where we wanted to find that height y. We turn this top part into a right triangle because this is a right triangle, and we know this angle, and we know this is 90, although that's not a very good right angle there. And we know the hypotenuse. We should be able to solve for this short side right here. I'm going to call this A from here to here. I'm going to call that A. A for adjacent. It's adjacent to the angle. Why does that matter? Well, if we can find A, and we know the length of this whole pendulum rod, we can then solve for the bottom, just subtract and solve for the bottom part right here. We're basically going to be saying that L, the length of the whole rod, is A plus delta y. Okay, well, if we want to find delta y, then that means that delta y is going to be L minus A. So let's set about solving for A, this short side of the triangle right here. Okay, well, we have an angle, we have a hypotenuse, and we have the adjacent side. In fact, let me just redraw this right here. I'll just redraw the top part. Okay, it may not be exactly the same scale. That's still 42 degrees right there. Our hypotenuse is 0.75 meters, and we want to find side A. And we know that's a right triangle. Or, yeah, it's a right angle. So we want to solve for A. Well, we can use a cosine. Cosine of an angle is going to be the adjacent over the hypotenuse. So we've been calling the hypotenuse L. So if you want to call it that, adjacent over L. Well, so if we want to solve for A, we simply say that A is L times the cosine of that angle theta. Or really 0.75 times the cosine of 42 degrees. And that'll give us A. What is A? 0. Multiply that out. 0.5. I'm going to take it out to 3 decimal places. 5.7. 557 what? 557 meters. Make sure you always write in your units. Okay, let's put just a dotted box around that. That's not a final answer, but it is important. And we can find y now by saying, okay, let's say, okay, if delta y is going to be L minus A, then that means That's going to be, what's L? 0.75 meters. 0.75 meters minus 0.557 meters. And that means that delta Y is going to be equal to what? 0.193. 0.193 meters. That's really going to be important, even though it's not the final answer. All right. We care about Y because we need to know what this height is so we can find the potential energy that was gained by this pendulum and bullet system. So let's go about doing that. That should be pretty easy. We know that the potential energy gained going upwards is mgy. Let's just simply multiply it out. Okay, this is going to be m right here. Now, what is the mass of the whole system? Well, that's m, that is the mass of the bob, capital M is the mass of the bob, plus the mass of the bullet itself, big M plus little m. So that's going to be 1.5 kilograms plus 0.05 kilograms. Okay, that's our mass in kilograms times gravity. We know that. Gravity. Oh, yeah. We know gravity's G. What is the value of gravity? 9.81, right? 9.81 meters per second squared times our newly found delta Y, which is that right there, 0.193 meters. That'll give us our potential energy gained going upwards. And what is it? MGY is 2.93. 2.93 what? 2.93 joules. I'm going to put a box around this because this was our goal for part 1, to find what the potential energy was that the bullet and bob system gained by going upwards. Again, we can use potential energy to find out what the original kinetic energy was, and from kinetic energy we can find out what the initial momenta of the two objects were. So that's it for now. We have this. This is important. We're going to use this to start in the next part of the video problem. And so I'll see you guys then.